All right, howdy. So welcome to my recording of a double lecture for both Friday and Monday. And in this double lecture, I am going to talk about determinants a bit more, and I'm also going to talk about some applications of them. So the first thing I want to pick up with is basically a result I kind of talked about last time, but I didn't give it enough justice. So before I get to it, I want to do a warm-up. So in the warm-up, let me choose a matrix. Maybe we will take the matrix 5, 6, -1, 3, 2, 4, 7, 8, 0. And we have this matrix M. And what we'd like to do is we would like to compute the determinant of M. And the way I talked about last time was this technique of cofactor expansion. So what you have to do is you use the following formula. If your matrix is like A11, A12, A13, A21, A22, A23, and A31, A32, and A33. Then the formula I talked about last time involves looking at the first row and for each of the entries in the first row, you compute a corresponding cofactor. And then you take their sum. And so if this is n, the determinant of n ends up being equal to the sum, well, in this specific case, A11 times the cofactor A11 plus A12 times the cofactor A12 plus A13 times the cofactor A13. And we did several computations along these lines last class, but as a way of warming up today, let's do one more. So let's look at our specific matrix, this one right here. What we need to do if we're going to use this cofactor formula for the determinant is we have to compute the A11, or the big A12, big A13. And in order to do that, we have to look at various minors of this matrix. So we will look at the minor M11, which corresponds to taking your matrix M and excluding the first column and the first row. So this ends up being 2, 4, 8, 0. Likewise, we'll look at M12, which corresponds to excluding the first row and the first column. So 3, 4, 7, 0. And then finally, we will look at M13, which corresponds to looking at the first row and excluding the third column. And in that case, we get 3, 2, 7, 8. And now for each of these, I have to compute the corresponding determinant and then multiply by a sign. So A11 here is going to be equal to -1 raised to the 1 plus 1 times the determinant of M11. And I can compute that just by looking at this. 2 times 0 minus 4 times 8 times +1 is -32. Likewise, I can go look at M12 and I can compute its determinant. 3 times 0 minus 4 times 7, which will just give 28. And this time A12 is going to be equal to -1 raised to the 1 plus 2 times -28 which is precisely going to be positive 28. And then finally, for M13, A13 is going to be equal to negative 1 raised to the 1 plus 3 times the determinant of M13, which in this case is going to be 3 times 8, so 24 minus 14, and then times a positive 1, so 10. So I've now computed the corresponding cofactors of interest. This one, and this one. So the determinant of M is thus going to be equal to 5 times A11, so 5 times negative 32, plus 6 times 28, and then minus 1 times 10. And if you wish, you can simplify this, but this is a good enough answer for me. And that's the determinant. So I want to note the procedure that we just executed kind of depended on an arbitrary choice, which is we were giving special attention to the first row, as you can see by the presence of little a11, little a12, and little a13 in this formula. So we were doing a cofactor expansion along the first row. But it turns out that you can compute the determinant by doing a cofactor expansion along any row. In fact, you can also do it by a cofactor expansion along any column. And that follows from the fact that we proved last time, which I'll just state again, that the determinant of A is equal to the determinant of A transpose. And because rows of A correspond to columns of A transpose and vice versa, a cofactor expansion along a column of A corresponds to a cofactor expansion along a row of A transpose. So I'm going to give you the general formula right now. And the significance of it is going to become more and more clear as we go today. But here it is. If A is any n by n matrix with n greater than or equal to 2, then the determinant of A can be expressed as a cofactor expansion using any row or column of A. And here's the general formula. This one right here is a cofactor expansion along a row. And this one right here is a cofactor expansion along a column. Okay. So this will be very, very useful for us. And it's going to come up again and again today. When we're computing the determinant in the proof of various theoretical results, the way we're going to do it often is we're going to take advantage of choosing the right row or column by which to do the cofactor expansion. To start, we will prove the following result. Lemma, let A be any n by n matrix, and let AJK denote the cofactor of AJK for k equal 1 through n. Then we have the following formula. So to understand why this formula is true, we're going to look at a following matrix. We're going to call it A star. Or maybe I'll denote it with a superscript. And the matrix will look like this. We'll have A11, A12, blah, 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 A1n. And then we go down and we get to AI1, AI2, blah, 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 AIN, And this will be, of course, the ith row. And now we keep going down further until we get to the jth row. And now in the jth row, we're also going to have A, I1, A, I2, blah, 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 AIN. And then, finally, going all the way down to the bottom, we have A, N1, AN2, blah, 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 ANN. So we have this matrix. And what we can do is we can make some observations about it. So last time I proved a result, which just to show you guys right now, so you guys can see it. If you have a n by n matrix, and it has two identical rows, then it follows that the determinant of A is equal to 0. So this matrix, or over here, has two identical rows. So it has to follow that the determinant of A star is equal to 0. And because that's true, well, we can do a cofactor expansion along a row of our choice. In this case, we're going to do the cofactor expansion along the jth row, in which case we see that this cofactor expansion will be A, I1, cofactor J1, plus A, I2, cofactor A, J2, plus blah, 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 AIN, cofactor AJN. And this shows that if I is not equal to J, then this determinant of this matrix, A star, is equal to this expression. But by our previous result, we know that this determinant also has to be 0. So this proves the case for when I is not equal to J. And if I is equal to J, then the expression is the ordinary cofactor expansion. Of det A. And you can see that just by looking at the formula on the previous slide. And so that completes the proof of this lemma. Now, I want to go into kind of proving some various facts about determinants. And they're all going to depend on this lemma. In particular, I want to consider row operations. So let me just remind you of the row operations. So cover them way back when. Way back here. Here we go. So these row reductions came up when we were studying the methods of solving a linear system. You could interchange two rows, you could multiply a row by a non-zero real number, you could also replace a row by its sum with a multiple of another row. And for each of these row operations, we associated a corresponding elementary matrix. And we showed that basically performing a sequence of row operations corresponds to a sequence of matrix multiplications by the given elementary matrix. So here's what we want to show. This will be our goal for the next little bit. For each elementary matrix E, we have the determinant of E times A is equal to the determinant of E times the determinant of A. This is our goal. And we will start by studying the case of simply interchanging two rows. Okay, so suppose Eij is the elementary matrix that swaps row I with row J. Then the determinant of Eij is going to be equal to -1, and the determinant of Eij multiplied with the matrix A is going to be negative the determinant of A. Let's try to see this in a specific case. So, suppose we look at a 3x3 matrix. Maybe A11, A12, A13, A21, A22, A23, A31, A32, A33. And then we swap the first row and the second row. This will correspond to the elementary matrix E12, and it will look like this: 0, 1, 1, 0, 1, 0. And if you want, you can do a cofactor expansion on the bottom row here. And after doing a cofactor expansion and looking at the determinant of this 2x2, you can see very quickly in this specific case, the determinant of E12 is equal to 0. Now, let's look what happens after we apply E12 to A. Well, now we'll have A21 here, A22, A23, and then here we'll have A11, A12, A13, and the bottom row will remain the same. A31, A32, and A33. Now, let's compute the determinant by doing a cofactor expansion of each of these along the bottom row. Well, then I would have det A is equal to A31, and then times the determinant of this block. So A12, A13, A22, A23, and then plus, actually, sorry, minus A3, 2 times the determinant of this and this. So A11, A13, and A21, A23. And then finally, plus A33, the determinant of A11, A12, A21, and A22. So this gives us an expression for the determinant of A. Now note that if instead we were taking the determinant of E12, what we'd have to do is take this expression and we'd have to flip the corresponding rows of this with this, this with this, and this with this, corresponding to the fact that the rows are flipped here. But you know from the formula from a determinant that if you flip the rows of the top and the bottom, or at least from the formula of a 2 by 2 determinant, it flips by a sign. So by flipping rows, each of these expressions would change by a sign. So that's how you can see right away that this statement is true, at least in this very specific case. The general case is basically proved the same way by induction. So the general case follows by induction on the size of the matrices. Okay. So that takes care of row operations of type 1. The next one we want to look at is row operations of type 2. So in this case, suppose E alpha, alpha not equal to 0, is the elementary matrix associated with multiplying maybe I'll give another subscript, I, with multiplying the ith row by alpha. Then we know that E alpha I looks like this. We have 1s along the diagonal until we get to the ith row, and then we have an alpha, and then we have 1s, and we have 0s everywhere else. Well, we know something from last time. So let me remind you guys. Should be down here somewhere. Okay. Here we go. If you have a triangular matrix, then the determinant of that triangular matrix equals the product of the diagonal elements. I proved that for you guys last time. And as a consequence, we see that because this is a triangular matrix, the determinant of E alpha I is simply equal to the product of everything along the diagonal, which in this case is just equal to alpha. Now, if A is an n by n matrix, then we can compute E alpha I times A, or rather the determinant of it, by a cofactor expansion along the ith row. Now, the ith row is all getting multiplied by alpha, so the determinant of E alpha I times A is simply going to be alpha times A I1 times the cofactor I1 plus blah 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 alpha times A n, or sorry, IN times the cofactor IN, and we can simply factor out the alpha here from every term appearing in this expression, and we see that this is alpha times the determinant of A, which is the same as the determinant of E alpha I times the determinant of big A. So now we have succeeded in verifying this claim for both row operations 1 and row operations 2. All that remains is to verify it for row operation 3. So for row operation 3, give me 1 second. Suppose E, I, J, comma, M is the elementary matrix adding M times row J to row I. Then, well, I claim that the determinant of such a matrix is going to be 1, but to see why it's 1, it's useful to actually write down what the matrix itself looks like. And if you do that, you'll get something like this. You'll get 1s down the diagonal, and this will be the ith row. This will be the jth row. And what we're doing is we're adding M times row J to row I, so we need to put an M here. And then we put zeros everywhere else. Now, if you look at this matrix, you can see right away that it's upper triangular. And the only thing along the diagonal is 1s. So the determinant of E, I, J, M is just going to be equal to 1. And that again follows from the statement we proved last time. Now, the next thing we need to do is we need to take an n by n matrix A, and we need to show that the determinant of E, I, J, M times A is simply equal to the determinant of A. Now I'll do that on the next slide. EIJM times A, where A is an abstract matrix, ends up looking something like this. You have A11, and then you have A12, blah, 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 A1n, and then you go all the way down until you get to the ith row. And here you're going to have A I1 plus M times A J1 plus blah, 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 all the way until you get to A IN plus M A JN. This is the row that was changed because you added the jth row times M to the ith row. And then you keep going down till you get to the bottom, and you have A and 1, A and 2, all the way over until you get to A and N. And what we're going to do is we're going to compute the determinant of this thing by doing a cofactor expansion along the ith row. The determinant of EIJM times A is going to be equal to the sum from I equals 1 to N of A, I should use a different index here. I'll use the index K. AIK plus AJK times M multiplied by the cofactor AIK. And this can be split into two sums. The first sum goes from K equals 1 to N, and it's AIK times the cofactor, big AIK, and then plus M times the sum from K is equal to 1 to N of AJK times the cofactor AIK. Now, we can study this expression. And the way we'll study it is we'll go back to the statement we proved earlier, namely lemma 2.21. Now, this lemma tells us some things. It tells us that the first term right here is actually just going to be equal to the determinant of A. But it also tells us that because I is not equal to J here, this second term, or this second sum, is going to be equal to 0. So this is det A, and this is 0. So we're able to conclude from this that this is equal to this. And that proves exactly what we wanted, because we know that the determinant of this matrix is equal to 1. All right, so that was a lot of conceptual work, but it's going to pay off like an incredible amount. So let me start to show you how it pays off. Here's our first example. Suppose a matrix A can be put in upper triangular form using only row operation 3. The one where you basically add a multiple of a row to another row. Then the determinant is the product of the diagonal entries. So, let's see how this works in practice. I'm going to start with a matrix. My matrix is going to be A. And here I'll have a 1, 2, 3, a 1, 3, 5, and a 1, 3, 7. So I want to compute the determinant of A. Well, the way I learned about doing it last time, I could do this via a cofactor expansion. But now I have a very, very powerful tool in my arsenal, namely the claim I made here. Because whenever I apply row operations of type 3, I'm not changing the determinant. So what I'm going to try to do is I'm going to try to use type 3 row operations to put this matrix in upper triangular form, and then basically just take the product of the resulting diagonal entries. So what I do here is I set row 2 equal to row 2 minus row 1, and row 3 equal to row 3 minus row 1. These are both type 3 operations. And after I do that, I'm going to still have a 1, 2, 3 on top. And now I'll have a 0, 1, 2. And I'll have a 0, 1, 4. And again, I can perform another type 3 operation. And I can set row 3 is equal to row 3 minus row 1. If I do that, I get this matrix, 1, 2, 3, 0, 1, 2, and then 0, 0, 2. And I can compute that the determinant of this is just equal to 2, because it's an upper triangular matrix and the entries along the diagonal are 1, 1, 2. So the determinant has to be this product of these 3 entries, and that's just 2. And according to the result I just proved, it follows that the determinant of A is equal to 2. Let's verify this using the other method we know, the cofactor expansion. So let me take all this, and I'll go to another slide, and I'll compute this the other way. So if I compute this the other way, I would have to look at M11, M12, M13, and I'd have to write down all 3 of these matrices. M11 here is going to be 3, 5, 3, 7. M12 is going to be 1, 1, 5, 7. M13 is going to be 1, 3, 1, 3. And I can see right away that the cofactor, big A13, is going to be equal to 0 because the determinant of this matrix is 0. A12 is going to be equal to -1 times the determinant of this matrix. So -1 times 2. And then I have to figure out A11. So I have to look at the determinant of this matrix. So 3 times 7 minus 3 times 5 is 6, and so this will just be positive 6. So the determinant of A is going to be equal to 1 times 6 plus 2 times negative 2 plus 3 times 0, which is just going to be equal to 2. So we've now computed the determinant of this matrix in 2 ways. But we see that regardless of which approach we take, we get the same number in the end. However, the way we did up here is vastly more efficient. To understand how much more efficient this method is, this one based on type 3 row operations, there's a table in the book that I want to share with you guys. Here it is. If you're computing the determinant using cofactors, say of a 10 by 10 matrix, you need 3 million additions, roughly 6 million multiplications. Whereas if you're doing it via elimination, you need roughly 300 additions and 300 multiplications. So elimination is vastly more effective. The only time the cofactors kind of outshine it is for very small n, namely n equal 2 or n equal 3. Let's do another example of this method. Maybe we'll go up and we'll look at a 4 by 4 matrix. So let me choose one. I'll just steal one from the book, actually. I will take this one right here. Actually, this one. So what I want to do is I want to compute the determinant of this matrix. And the way we're going to approach it is we're going to approach it using elimination. Now, there's something to be noted about this. We can't use elimination naively simply using type 3 row operations. The reason we can't do that is because we have a 0 here. And whereas when we're usually doing elimination, we subtract the first row from the ones below, and then we subtract a multiple of the second row from the ones below, etc., etc. Because we have a 0 here, we immediately run into trouble. So computing det A, well, we can't compute it from row 3 operations alone. Now, that would be a problem, but we have other types of row operations as well. Namely, we have type 2 operations and type 1 operations. Now, type 2 operations are not going to help us because in this specific example, you can't multiply the first row by anything to get rid of the 0. But you could use a type 2 operation or a type 1 operation to swap rows. The only thing you have to keep in mind is that whenever you do a type 1 operation, you're changing the determinant by a sign. So I'm going to go through the process. And the first thing I'm going to do here is I'm going to swap row 1 with row 2. And this is a type 1 operation. So as a way of signifying that I'm altering the determinant, I'm going to put a -1 here. I'll need to remember this for later. But after I do this, I have 1, 1, 1, 1, 0, 1, 2, 3, and then -2, -2, 3, 3, and then 1, 2, -2, -3. And this is much better because now I have a 1 here, and that gives me something to work with. So what I'm going to do is I'm going to set row 3 equal to row 3 plus 2 times row 1, and row 4 is going to be equal to row 4 minus row 1. And we do both of these operations in a single step. First row stays the same, as does the second row. And when I do this operation, this will die and this will die. And I'll end up with a 5 and a 5 here. And then I'll have a 0 here, a 1 here, a -3 here, and a 4 here. Okay. So this is a better shape. Again, what we want to do is we want to kind of consider performing another type 3 row operation to try to move this matrix into upper triangular form. So I can subtract the second row from the third row. So I can, or fourth row. So I can set row 4 equal to row 4 minus row 1. And if I do that, I'll get 1, 1, 1, 1, 0, or I'm sorry, I want to subtract row 2. 0, 1, 2, 3, 0, 0, 5, 5, and then 0, 0, -5, and then I'm subtracting 3 from 4, so I'll just have a 1. All right, now this thing is almost in upper triangular form. The only problem is this -5, and I can get rid of it by doing one more type 3 operation. So I can set row 4 equal to row 4 plus row 3. And if I do that, I get this matrix. Oops, sorry, that -5 should go away. So I have a 0 here, and now I will get 5 plus 1, which is 6. All right. After doing this sequence of operations, I have reduced the matrix to something that is upper triangular. And I can readily compute the determinant of this matrix. 1, 1 times 5 times 6. The determinant is, or if this is A star, the determinant of A star is equal to 30. Now I want to be able to infer something about my original matrix A all the way back up the ladder. I can do that, I just have to remember the one key fact, which is back here I swapped 2 rows. So, because I swapped 2 rows, I have to take the determinant down here, and I have to multiply it by -1. And if I do that, I find that the determinant of A here is -30. And that completes the computation. So what I want you guys to notice is how much simpler this is than cofactor expansion. If I was doing a cofactor expansion, I'd have to like kind of pick a row or column, work my way around it, and then compute 4 different cofactors of 3x3 matrices. And for each of those cofactors, I'd have to do a cofactor expansion of the 3x3 matrix itself, and it would require a ton of operations. But using just a handful of row operations on A, I'm able to take it, produce this matrix A star, where the determinant is readily evaluated based on the fact that it's upper triangular. So, going forward, this is definitely the best and most practical way for computing determinants. The only thing you really have to keep in mind is the subtleties of using row operations that are not type 3. Like, you have to always keep in mind that if you're swapping 2 rows, a negative sign is getting introduced somewhere along the way. So I'll state the final conclusion here. We can effectively evaluate determinants using row operations. And keeping track of any operations that alter the determinant. All right. So now what I want to do is I want to look at some more theoretical applications of the result we proved above. So give me 1 second. All right. Let's prove this result. So we make the following claim: an n by n matrix A is singular if and only if the determinant of A is equal to 0. So we can prove this as follows. We may write A as EK times EK minus 1, blah, 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 E1 times F, where the EI are elementary matrices, thus have non-zero determinant. And F is a matrix in row reduced echelon form. In this decomposition right here, this comes from Gauss-Jordan elimination, which was the subject of our lecture about a week and a half ago. Now, here's the key fact. Because F is a matrix in row-reduced echelon form, if F is not equal to the identity matrix IN, then F has a row consisting of zeros. Okay. Now, let's note the formula that we just proved. For an elementary matrix, we have the determinant of E times B is equal to the determinant of E times the determinant of B. So, in our specific case, we're going to have the determinant of A is equal to, by iteratively appealing to this formula, the determinant of A is going to be equal to the determinant of EK times the determinant of EK minus 1, blah, 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 the determinant of E1 times the determinant of F. Now, all of these determinants of elementary matrices are not zero. The reason they're not zero is basically what we proved before. And because they're not zero, the only term that remains to kind of study is the determinant of F. But if F is singular, then when you put it in row-reduced echelon form, it has to have, it can't be equal to the identity matrix, and thus it has to have a row of zeros. So, it follows that the determinant of F here has to be equal to 0, which implies the determinant of A has to be equal to 0. So this shows that if A is singular, then the determinant of A is equal to 0. So we've now proven half of this theorem, but the theorem has another half as well, which it says that if A is not singular, then the determinant should not be 0. This part's really easy to prove. So suppose A is non-singular. Then A inverse exists, and the determinant of A, the determinant of A times A inverse is the same as the determinant of IN, where this is the identity matrix, so it has just ones along the diagonal, which is 1. And the determinant of A times A inverse is equal to the determinant of A times the determinant of A inverse. And so if you combine this line with this line, it follows that the determinant of A is not equal to 0. Now, the one thing I really have to justify here is this assertion. Because as of right now, I only know that we have this identity for any matrix B and an elementary matrix E. So I don't know this to be true yet, but I can prove it. Here's how I can prove it. In fact, I'm going to prove something more general than it. Okay, so suppose A is a non-singular matrix. Then after we kind of put it in row-reduced echelon form, we can write A is equal to EK times EK minus 1, blah, 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 E1 times IN. And if we do this, then we can look at the determinant of A times B. Well, this will be the same thing as the determinant of EK times EK minus 1 times blah, 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 E1 times IN times B. But now if you multiply the identity matrix by B, you just get B. So this is the same thing as the determinant of EK, EK minus 1, blah, 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 E1, B. And now I can iteratively use the identity I already know, namely that the determinant of E times B is equal to the determinant of E times the determinant of B. And from this it follows that this is the same thing as the determinant of EK times the determinant of EK minus 1, blah, 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 determinant of E1 times the determinant of B. Now, I can also go the other way, and I can simply look at this expression, and I find something similar, which is I find that the determinant of A is equal to the determinant of EK times blah, 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 the determinant of E1. Now, granted that this is true, and the proof is the same as basically this, I can see that this thing right here is the same as the determinant of A. So the determinant of the matrix A multiplied by the matrix B turns out to be the same thing as the determinant of A times B. And this is true in general. So now I can go back here and I can apply this to a very special case. Namely, A is non-singular and A inverse exists. So I use this identity, which follows from the thing we just proved, and from this I see that the determinant of A is non-zero. However, the thing we just proved it has a lot of philosophical significance. And so I kind of want to sit here and stress it for a minute. The property that the determinant of A times B is equal to the determinant of A times the determinant of B is possibly the single most important thing about the determinant. Because think about it. Right here, we're multiplying two matrices, A and B. But somehow when you take the determinant of matrix multiplication turns into the determinant, or turns into the multiplication of two real numbers. Let's demonstrate this. Suppose I have two matrices, A and B. So maybe A here will be 1, 5, 6, 4, and B here will be 1, -1, -2, +1. Let's compute the determinant of each of these individually. Well, the determinant of A here is going to be 4 minus 30, so -26. The determinant of B here is going to be -1. So we expect that if we multiply the matrix A and the matrix B and we take its determinant, the determinant should be 26, well, -26 times -1, which is +26. Let's see if this actually pans out. So I can try to take the product of A and B. Here I'll have 1, 5, 6, 4. And here I'll have 1, -1, -2, 1. And if I take this, this matrix multiplication, I'm going to get -11, 5, -3, and right here I will get -1. So now I need to take the determinant of the product, so this matrix, and this will be 11 minus 3, or -3 times 5, which will precisely be 26. So this demonstrates the formula in practice. The other result, the one we proved before we were looking at this formula, is also very theoretically significant, because it tells you that one way to kind of test if a matrix is non-singular is to simply take the determinant of it and see what it looks like. Okay. So, let me see what else I want to cover from this section, if anything. All right. I think I'm good here. So let's move on to 2.3. In 2.3, we're going to look at a very, very interesting matrix called the adjoint. So let's let A be an n by n matrix. As usual, we'll write it like this. We have A11, A12, blah, 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 A1n, A21, blah, 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 AN1, and then all the way over to ANN. And from this matrix A, we're going to form another matrix called the adjoint. The adjoint of A will be defined as follows. What you do is you fill it up with little things that we've already seen, namely cofactors. So here in the 1, 1 entry, we'll put the cofactor A11. here, right here in the 1, 2 entry, we'll put the cofactor A12. Likewise over here, A21, blah, 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 blah. Capital A, N1. Capital A, NN. And capital A, 1N. So I have a matrix A, and from it I can form another matrix called the adjoint. The adjoint is really cool because it does something that's kind of fascinating, which we'll now show. If you take A and you multiply it through by the adjoint of A, what you get is you get the determinant of A multiplied by the identity matrix if A, well, actually this is true in general. So I want to verify this identity to begin with, and then we'll look at some applications of it. So to verify this identity, what we can do is we can appeal to the thing we started today with, the original results, namely the fact that, where is it? Or the fact of lemma 2.21. So lemma 2.21 tells us that if we look at this sum of like AI1, AJ1, blah, 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 this sum will be equal to the determinant of A if I is equal to J, and 0 if I is not equal to J. But here's the key fact. The ith J, or the ijth entry of the product A with the adjoint is exactly this sum. So this tells us that for these entries, when I is not equal to J, we get 0. And when I is equal to J, we get the determinant of A. So, consequently, the only things that have the potential to not be 0 are along the diagonal, and all of those things have to be det A, which is how we get this formula. All right, so really this formula is just kind of an incarnation of lemma 2.21. Now there's kind of an important theoretical corollary to it, which makes it really, really useful. So suppose A is non-singular. Then the determinant of A is not equal to 0. We've already proved that. And A inverse is equal to the adjoint of A times 1 over det A. The reason this is true is that when you multiply A by the adjoint of A and you divide by 1 over the determinant of A, you get precisely the determinant of A times the identity matrix, and then multiplied through by 1 over the determinant. So this will cancel out with this, and all that will be left over is the identity matrix. So this gives us an expression for A inverse, which is really cool because the only way we had previously known how to go about computing A inverse was essentially to basically do Gaussian row reduction to a certain kind of augmented matrix. But now we have an explicit formula. So let's do an example. Suppose I look at the following matrix. Maybe A equals, let's see, how would I steal something from the book? I want to steal something relatively simple, not something too hard. All right, I'm going to steal this matrix right here. That's too easy. I'll make my own. Okay, so I'm gonna go with the matrix 1, 3, 5, 6, maybe I'll go with here, 1, 4, 10, 5, 8, 2. And what I want to do is I want to compute the inverse. So I want to compute A inverse using the adjoint. So one thing that's necessary for this is we have to find the determinant of A. So the first thing I'm going to do is I'm going to try to find the determinant of A, and really just to make my life easier, put a 1 here. So in order to do that, I'm going to run through the same kind of operations that I was doing before. So I'm going to set row 2 equal to row 2 minus row 1. Row 3 is going to get set to row 3 minus row 1. And if I do that, I get this matrix. 1, 3, 5, 0, 1, 5, and then 0, 5, and negative 3. So these are both type 3 operations. And now what I can do is I can subtract 5 times row 2 from row 3. And if I do that, I'll have 1, 3, 5 for the top row, 0, 1, 5 for the second row, 0, 0 for the third row, and the final entry will be 5 times 5 subtracted from negative 3, so negative 28. And thus we can see that the determinant of this thing is the product of the entries in the diagonal. So if this is A star, the determinant of A star is equal to negative 28, which means the determinant of A is equal to 28. All right, so we have already kind of solved one of the things that we need to know to compute the adjoint. But the adjoint is also going to involve a lot more computation because we have to compute a ton of different cofactors. So let's take what we have now and go to a new slide. So I have to compute A11. This will be the same thing as negative 1 times the determinant of the minor M11, which in this case will be 4, 10. 8, 2. And if I compute this, I get 8 minus 80, so I get negative 72. And then I have to compute A12. This will be negative 1 to the 1 plus 2 times the determinant of this minor. And so here I'll get 2 minus 10, so negative 8, but times negative 1, so positive 8. And then I'll compute A13, and this will be negative 1 raised to the 1 plus 3, and then times 1, 1 for 8. So I'll get 8 minus 4 times positive 1, which is 4. Now I have to compute a lot more things as well. So next thing I have to do is I have to compute A21, and then A22, A23. And then after that I'll still have to compute 3 more things. But here I'll have negative 1, 2 plus 1, negative 1, 2 plus 2, negative 1, 2 plus 3. And A21 is computed by getting rid of the second row and the first column. So I'll have 3, 5, 8, 2. And this will end up being 6 minus 40, so negative 34. And times negative 1, so positive 34. And then here I'll have, so this is getting rid of the second row and the second column. So 1, 5, 1, 2. The determinant of this is going to be negative 3, and then times positive 1. And then here I'm getting rid of the second row and the third column. So what I do here is I put, hold on, my mind is starting to blank. I might need to take a break after this example. A23. So here I'll have 1, 3, 1, 8. And if I evaluate this determinant, I get 8 minus 3, so that's positive 5, but times a negative 1, so negative 5. And next I have to compute A21, A22, A23. So I have to compute A31, A32, and A33. So this will be negative 1 to the 3 plus 1 times, so it corresponds to getting rid of the third row and the first column. So 3, 5, 4, 10. If I evaluate this, I get 30 minus 20, so this should just be 10. Here I'll have negative 1 raised to the 3 plus 2. And here I'll put, let's see, what goes here? Get rid of third row, second column. So 1, 5, 1, 10. So 10 minus 5, but times negative 1, so this will be negative 10. And then for A33, I'm getting rid of third row, third column, so I'll have -1 to the 3 plus 3 times 1, 3, 1, 4. And if I evaluate this, I'm going to get 4 minus 3 times +1, and I get 1. Okay, so this was extremely laborious, but I've now computed all of the cofactors. And now that I have all of the cofactors and the determinant, it's just a matter of arranging them into the formula. So I will do that in 1 second. So let's go back to the formula. Oh, crap. I just have to fix one thing here. This is not quite right. I messed up my indexing. This should be a 2, 1, and this should be 1, 2. Likewise, down here, this should be 1n, and this should be n1. So the indexing is the opposite of the conventional, but that's fine. Okay, so now I can write down the inverse of A in this specific case using all my data. So A inverse is going to be equal to 1 over 28 times the following matrix. These entries are going to correspond to the first column. So -72, 8, and 4. These entries are going to correspond to the second column. 34, -3, -5. And then these entries are going to correspond to the final column. 10, -10, 1. So, using the adjoint matrix, we're able to compute an expression for A inverse. So, let's just get them both in the same slide so we can kind of look at them together. I don't necessarily want to verify that this is the inverse because it's kind of a long computation, but we can check at least one entry or so to make sure we did everything correctly. So this is our original matrix A. So let's think about what happens if we multiply the first column here with the first row here. Well, then we would get -72 plus 34 plus 10, all divided through by 28. Is this correct? So maybe there's something off in my calculations. Either way, I'm going to take a brief break and I will come back in a little bit and I'll pick up with this example and continue on and show some more applications of the determinant.